Hello, Mr. Sorrentino here again, and I'm presenting another one of these videos from the Math 31 series, and this one deals with 6.3 matrices and systems of equations. So in 6.1 and 6.2, we learned methods of using elimination and substitution to solve systems of equations. When I have two equations with two unknown values, that's not a big deal. I mean, it works pretty well. I can make good decisions really quickly. When we try to use a similar process of elimination and or substitution, when I start getting three equations with three unknown variables, or even if we were, God forbid, given four equations with four unknown variables, or even more than that, the process of using elimination and substitution would be much more lengthy and time consuming as a result. So there are other methods to solve a system of equations in a little bit more of a streamlined fashion. And as we move through these subsequent chapters, we're going to learn different ways of dealing with this that get a little bit more streamlined as we move along. Not to say there's going to be some parts that are going to work slowly and deal with some calculations you have to be careful of, because it's easy to make a mistake on early steps that could affect the later steps, and then throws your entire answer off. And so we use matrices as a method of doing this. And I don't have a kind of formal definition of it, it's in your textbook, but an augmented matrix is basically me taking a system of equations like A. Now I want to make sure as I do this, I'm going to put a couple little formatting things down here. One, I want to make sure that the system has variables lined up. That means I want to be able to see, like, a solid, column of X's, a solid column of Y's, a solid column of Z's, all lined up underneath of each other. If I don't have that, I really should maneuver things around first to make sure that's happening. Now in A, it happens to be the case it is happening. The second thing I do is I write the symbol down for an augmented matrix, which an augmented matrix is going to have brackets, and I want to make these are going to be bigger to have enough room for these numbers. And I have a vertical bar in the middle of it. So it's going to be much bigger for this because I'm going to basically make this take the place of this equation, or system of equations, I should say. The left side are the coefficients only. So the 2 and the 4 here, the 3 and the -5 here. And then, of course, the right side are the results, or essentially the numbers that the equations are set equal to. So 5 and -1. And basically this lets me know that I have an X column and I have a Y column, and I have, of course, my result column when I do this. Now, and that's what an augmented matrix looks like. So what I would like you to do for part B is I would like you to write an augmented matrix for the system of equations you see in part B. Okay. Now, one of the things, again, that some students notice, or some students don't to pay attention to, is the very first thing. You have to make sure that your system of equations is lined up. So I want to have an X, a Y, and a Z column, so I want to be able to see them. This one has them in this order. And so does the second one. I have my X term, my Y term, and my Z term. The third equation, if you notice, doesn't have a Y term, and the Z term is coming first. So I really should rewrite this as -8x, because that negative is attached to the 8x term, not the 2z, plus, I don't have a y term, but I can think of it as being plus 0y, and I do have a positive 2z term. And so this would be a good rewrite for my system of equations in order to come up with the augmented matrix. The augmented matrix for this would then be 2, 4, -8, making up my x column, -1, 3, and 0, making up my y column, 4, -1, and 2, making up my z column, and my results column would be 12, 3, and -2. And so that would be the augmented matrix for part B. So that's usually the first step if you're going to use one of the methods of using matrices to solve a system of equations, is that you're going to rewrite the system of equations as an augmented matrix. What you do next, it depends on which type of elimination you're going to. It's considered an elimination process, and you're going to see it has some similarities to some of the things we did with elimination. It's just a little bit more directed in how you should carry it through. The first one we're going to talk about is Gaussian elimination. So let's see what that involves. Gaussian elimination is a set of steps that we perform to our augmented matrix until it reaches a certain structure that allows itself and lends itself to us knowing what the solutions will be for the system of equations. Now, I do this by performing row operations on my matrix. As I do row operations on my matrix, I have to keep in mind there's only certain things I'm allowed to do. When I do row operations, I can interchange any two rows. So if there's, and we're going to find out how do we know if we want to do that or not, but I can interchange any two rows. So I have to make sure I do that in their entirety. So, if I choose to move the, row 1 with row 2, I have to make sure that both parts, the coefficients and the result side, get moved accordingly. I can multiply an entire line by the same non-zero constant. I never want to multiply anything by 0, because if I have a row of zeros or a column of zeros, that could cause some major problems and actually could create situations where I have maybe no solutions or infinite solutions in a situation where I really only have possibly one. So I want to make sure I can multiply an entire line or an entire row by the same number. And the third thing I can do is that I can add a non-zero multiple of any row to another row. That kind of goes along with things that we did with elimination. Basically like multiplying the entire equation by 2 to make certain things match up and go away. And then I would add equations together to make the variable actually go away. That's what these row operations are more or less doing as well. These row operations make up, both Gaussian elimination and what they call Gauss-Jordan elimination. Gaussian, the only difference between the two is what kind of structure do you want your augmented matrix to look like before you say, okay, I'm done, I can start figuring out what the answers are. And here's what I mean. With Gaussian elimination, my goal is to convert the augmented matrix into row echelon form. In row echelon form, this is how they have a verbal description of it. If a row does not consist entirely of zeros, then the first non-zero element in the row is a 1, called a leading 1. For any two consecutive non-zero rows, the leading 1 in the lower row is farther to the right than the leading 1 to the higher row. All the rows consisting entirely of zeros are at the bottom of the matrix. If a fourth property is also satisfied, a matrix is said to be in reduced row echelon form, and we'll talk about what that is. Basically, row echelon form is this. In a 2 by 2 matrix, you're going to see I have this diagonal of 1s. And anything below each of the 1 is going to be a 0. That's what it's going to look like when it's done. I want it to look like that when it's finished. So I would do these row operations until I make it look like that. So let's have a look with this system of equations. And I'll demonstrate it on this one, have you try it on B. Now we've already done we've already done the augmented matrix for this, so I'm just going to rewrite the augmented matrix at this point. 2, 4, 3, -5, 5, -1. Now the procedure for doing this, you could do any of these things at any time, but here's the deal. Typically, when I go back to these steps that we mentioned before, these two, the method and the procedure that I use, these are the ones I use to establish my ones. This is the one I use to establish my zeros. Occasionally I might be able to use number 1 to establish a zero somewhere, but it's very rare. The other thing we want to keep in mind when we do this, I put a nice big star here. When we do these row operations on an augmented matrix, whether it's getting it to row echelon form or what we're going to talk about eventually, reduced row echelon form, I would like to establish the ones first, and then the zeros in each column. So it seems kind of weird. We're going to use row operations and focus on the rows, but we want to be transforming each column one at a time. So that means if I'm trying to get into, say, a situation with a 3x3 matrix where I have this kind of setup, I'd want to establish this column first. I would establish the 1 first and then get the 2 zeros, establish this 1 next and get its 0, establish this 1 last, and then I'd have it in my row echelon form. So that means that if I follow that general guideline, the very first thing that I want to change here is I want to change this into a 1. So I have to figure out, well, again, how am I going to do that? Well, I could, add some multiple of the row below, and that's not going to cause a difference here, but the simplest way would probably be to take 1/2 of row 1. I cannot just multiply one number in a row. I had to change an entire row in some way based off of this, whether I'm switching rows, whether I'm multiplying an entire row by a number, whether I'm adding a multiple of one row to another. I am changing the entire row as a result. And so what this becomes is 1, 3/2, 5/2, and I didn't do anything to row 2 yet. So I'm good. The next thing I want to do, maybe use a slightly lighter color here, is I want to establish the 0 here. Well, I'm not going to be able to multiply or divide to get to that 0. Certainly doing a row swap is not going to put a 0 down there because I only have a 1 in the same position, in the first position on this top equation. So I have to figure out that when I do my row operation, row 2, I'm going to subtract 4 times row 1. Now we said add 2 rows together or add a multiple. Remember, subtracting 4 times row 1 is like adding a -4 times row 1. And so when I do that, row 1 is going to be left alone. I'm not transforming row 1, I'm just going to use a multiple of it and add it to row 2 to transform it. And so if I do 4 minus 4 times 1, it gives me the 0 here. It should, that's what I wanted there. Negative 5 minus 4 times 3 halves will end up giving me a negative 11. Negative 1 minus 4 times 5 halves will also give me a negative 11. So I got this column all taken care of. If I keep following and doing the steps the way I transcribed, find my 1 first, establish that, then establish the zeros, then anything I do from here on out should not change the 1 and 0 I have in this first column. A common mistake that students do is that they start doing and defining row operations that are perfectly legal to do. They're not wrong in doing the row operation. At least they're doing the row operation correctly. It's just that they end up undoing what they had previously established. And if you don't have those 1s and 0s where they're supposed to be, and if you establish the 0 where it needed to be, and then you do the next step and it gets rid of the 0, it's basically counterproductive. So the next thing I'm going to do, in the last row operation I really had to do to get this in row echelon form, is I'm going to do negative 1/11 of row 2. I could also say divide by it, but the same thing. So 1, 3 halves, 5 halves is left alone. 0 times negative 1/11 is still 0. That didn't change. Negative 1/11 times negative 11 is going to give me 1. And of course I'm going to get a 1 over here as well. So I have this in row echelon form. Now what does this mean? Well, going back to when we wrote these in augmented form, remember this is my X column, this is my Y column, this is my result column. And each one of these had an X column, a Y column, and a result column. They got changed by doing these row operations. And so I have that going on down here. This row right here is telling me that if I have 0 X's plus 1 Y, that should equal 1, or simplistically, Y equals 1. This row, and I would usually start from the bottom row and work my way to the top. So if I had more rows, because it was a 3 by 3, I would start bottom, work my way to the top. This is saying that 1x plus 3 halves y equals 5 halves. Now knowing that y is 1, x plus 3 halves equals 5 halves. Subtracting 3 halves from both sides, I get x equals 2 halves, which also equals 1. So I could say for this that the solution is 1, 1. So here I'm using a very specific procedure and following that procedure through where I don't have to make decisions about x's and y's and what I should eliminate, which method should I use. I want to establish my column of 1 and 0s each way through, and that's going to help me figure out how to do the rest of it, how to get to the point where I can start solving this equation or system. So going on to part B, and reminding you the fact that this augmented matrix was written as 2, -1, 4, 12, 4, 3, -1, 3, -8, 0, 2, -2. Perform the steps necessary to put this in the row echelon form, and then solve this equation or system of equations, and then we'll go through it. Okay, now Again, just because it's more defined of a procedure doesn't necessarily mean that, there's not variations that you could possibly do. I mean, sometimes you might have more than one choice to do certain things along the way. So, the way I'm going to take care of it may not be the same way that you may have taken care of it, but as long as you're performing the row operations correctly and you do get down the row echelon form, everything should be fine. So, I'm just going to kind of scooch this over a little bit, leave more room for my row operations. The first one I'm going to do, now again, I want to establish the 1, which should go right here. I always do the 1, establish the 1 first for a column. So I'm going to handle column 1 first. And so my row operation, I want to turn that 2 into a 1 somehow. The easiest way to do that is I'm just going to take half of row 1. Which means that row 2 and row 3 are left alone. Half of row 1, half of 2 is 1. Half of -1 is a -1 half. Half of 4 is 2. Half of 12 is 6. So that's what I've transformed this into. Now I want to establish my zeros here and here. I'm going to indicate 2 row operations at the same time because I'm going to do similar things to get my zeros. It also saves some space. Row 2, I'm going to subtract 4 times row 1. Because if we think about it, 4 minus 4 times 1, and that's why I always choose the one that has a 1 in it. Because if I choose the one that has a 1 in it, then I'm able to, if I choose the one that has a 1 in it, it's really easy to figure out what I need to multiply the row by to get the number I need to subtract or add to the number. For row 3, I want to get rid of that -8 and make it 0, so I'm going to add 8 times row 1 because I want to do 8 times that 1 I have in row 1. So for this one here, row 1 is the only thing that's left alone here. If I do 4 minus 4 times 1, I get 0. That's what I wanted. 3 minus 4 times -2 gives me a 5. Because that ends up becoming 3 minus -2, which is 3 plus 2. -1 minus 4 times 2, well, -1 minus 8 is -9. 3 minus 4 times 6, well, 4 times 6 is 24. 3 minus 24 is a -21. Row 3, -8 plus 8 times 1 is 0. 0 plus 8 times -1/2 would give me a -4. 2 plus 8 times 2, that's going to be 2 plus 16, that's 18. -2 plus 8 times 6, well, 8 times 6 is 48, and -2 plus that is going to give me 46. So that's what I transformed it into. Now again, if I follow these steps the way that I've been doing, establish the 1 first and get the zeros in my column second, this column should remain unchanged as I go through the rest of this. That's important. Again, I could be doing correct row operations or legal row operations, but if I'm doing the wrong, if I'm not doing them in the right order, I could be undoing things I had done before and not get any closer to getting this in row echelon form. So now, the next thing I want to do is I'm going to go to column 2, and I want to establish the 1 here. That's where the 1 should go in the row echelon form, right? Remember, it should be a diagonal of 1s. So the row operation I'm going to need to do is I'm going to need to do 1/5 of row 2, or basically divide row 2 by 5. Which means when I do this row operation, the current row 1 is going to be left unchanged. the current row 3 is going to be left unchanged. It's just going to be row 2 that gets changed. So the 0 I had divided by 5 is still going to be 0. So that nothing happens there. 5 divided by 5 is going to give me the 1 I wanted. That's what I wanted there. Negative 9 divided by 5, I'm just going to write it as negative 9/5. And negative 21 divided by 5 is going to be a negative 21/5. So now, the next thing I want to do, first of all, notice this column untouched. Didn't change anything. And I want that to happen. The next thing I want is this to become a 0. So the row operation I'm going to do for this is I'm going to do row 3 plus 4 times row 2, because that's where the 1 is. I mean, theoretically, I could do row 3 minus 8 times row 2. The problem is that would make the 0 down here no longer be a 0. So I'm best doing the row 2 here because I do have a 0 in that position and not a 1 in the first row, in the first column position. So that's why that this is done really strategically, and it should be done in that order so that you're not undoing the work you did at each column along the way. I'm only changing the third row with this, so these 2 rows are left unchanged. Okay, 0 plus 4 times what's in row 2, 0, is still going to be 0. Negative 4 plus 4 times 1 is going to give me the 0. 18 plus 4 times negative 9/5 is going to give me 54/5. And 46 plus 4 times negative 21/5 is going to give me 146/5. I'm not showing all the computations that were done. You should be able to establish those on your own, but that's what they end up being. I'm almost done. The last thing I need to do to get this in the row echelon form is that this has to become a 1. And so my row operation, I'll just move it over this way so it doesn't get too low, is going to be, I'm going to do 5 over 54, the reciprocal, times row 3. Which means that, again, these 2 rows are going to be left alone. If I multiply this 0 by 5 over 54, I get nothing. If I multiply this by 0 by 5 over 54, I still get nothing. So the zeros I established still stay. Again, that's why I do this. I wanted these, I wanted what I had as far as the 1s and 0s go to remain unaltered from this point on. Because if they change and become anything else, then I don't have it in row echelon form, and that would cause me an issue. This becomes a 1, because 54/5 times 5/54 is 1. 146/5 times 5/54 becomes 146 over 54, which does simplify and becomes 73 over 27. So again, what this means is that this bottom equation means I have 0x plus 0y plus 1z equaling 73 over 27, which means z equals 73 over 27. No one's going to say that these are always going to be nice numbers, by the way. This equation here is the same thing as saying 0x plus y minus 9/5 z, which we know is 73 over 27, equals a negative 21 over 5. Of course, that doesn't really happen here, so y is going to equal negative 21 over 5 plus 9/5 times 73 over 27. And when I work that all out, y ends up being 2/3. And now I could either come up to here and do this one, or I could go up to one of the original equations. I'm going to choose to go with that because I have an equation here where if I just know what z is, I can figure out what x is. And so I mean, it's up to you. I mean, you could use this equation here, which is just another version of an equation that came about from elimination. And with these row operations, I'm performing the necessary operations that I'm making equivalent equations along the way. So I opted just to say, okay, well, 2 times z, which we established already to be 73 over 27 minus 8x equals a negative 2. Negative 8x equals negative 2 minus 2 times 73 over 27, which is a negative 200 over 27. And then dividing both sides by negative 8, I get 25 over 27. And so my solution is 25 over 27, 2/3, 73 over 27. So some pretty nasty numbers you have to deal with along the way, but as for answers, but kind of more of a procedure where it takes some of the decision making out of it. And for some students, that's a big plus because they'll sit there and stare at it and ponder over the decisions so long they really don't get any work done. And if it's during a test, that's not going to be all that useful to you. Now, the other method that I talked about was Gauss-Jordan elimination, which is practically the same procedure. The only thing that's different is I need to get it to a different point along the way. So let me show you what that is. When I do Gauss-Jordan elimination, I perform the exact same type of things as I did in the previous problems. The only thing that's different is that instead of stopping with just having zeros underneath these diagonals, I also have zeros on the top of those diagonals. The reason being is if I look at, say, for instance, the one on the far right here, which would have an x column, a y column, a z column, a w column, whatever the variables are. This would tell me essentially that x equals a, y equals b, z equals c, and w equals d. Because I would have an equation that has, the coefficient of 1 for one of the variables, 0 for the others, and it's going to be equal to a number. So that means basically just that variable equals that number. So that represents a solution. So so basically once you look at a augmented matrix written in Gauss-Jordan elimination and it's in reduced row echelon form on the left, you have your solutions in front of you. That's really the only other benefit from it. It does take more row operations, which, as you've seen, can take their share of time. So, that's the drawback, is that you do have to do more steps, But I mean, it kind of takes the place of the steps that you would be doing to take the value you got for, say, Z, plug it in to find out what Y is, and then plug those two in to figure out what X is. But, whichever one you feel more comfortable with, at a certain point, I usually just stop with the Gauss elimination, get it down to just row echelon form, and then just use substitution the rest of the way. But I'm going to demonstrate how to do this in example 3. But I'm going to let you have a chance first. Use either this Gauss-Jordan elimination, which is the same row operations we used before, you're just trying to get to a different point, or Gauss elimination, and try to solve this is of the equations we have down here. Let me scooch that up a bit. And once you get an answer and put it in, then we'll go through it. Okay, so if we're going to be using Gauss-Jordan elimination or anything else, we want to be able to, first write this as an augmented matrix. That's important. So I'm going to write this as an augmented matrix. The top row, 2, 1, 1, -3. The second row has a couple of pitfalls in it. No, first of all, it's missing a Z term, which means its coefficient is 0. I'll put the -17 over here already. It has the Y term and then the X term, so these are not lined up. Now, you don't have to write a whole step of lining this up like I did in the previous example. I just have to recognize that, well, there's a 5 with the Y, and there's a -1 with the X. Recognizing that as I write this out, I want to have an X column, a Y column, a Z column, and a result column. So as long as I'm aware of what variables have which coefficients, I don't have to rewrite the equation completely before I write the augmented matrix. And anything missing would be a 0. So like in row 3 as well, I don't have an X term, so I have no X's, 1 Y, -4 Z's, and that equals 13. So there is my augmented matrix. Now I kind of designed this one that, doing the steps I'm going to do, it's going to create situations where when I do a step, I actually get a couple things I need to have this in reduced row echelon form pop up on their own. It's not guaranteed that you're going to have problems that do that quite frequently. You're going to have to do steps along the way for all of them. But this is what I chose to do as far as my steps go. I chose, because I see, although it's a -1 right now, I do see a 1 involved in row 2. So I chose to swap row 1 and row 2. So I'm going to have -1, 5, 0 on my top row with the -17 following it. The 2, 1, 1, and -3. And of course the 0, 1, and -4 equaling 13 is unchanged. I almost have my 1 in that position. If I just simply take row 1 now, the new row 1, and multiply it by -1, then I'm going to have 1, -5, 0, +17. And of course, the rest of this is unchanged because I didn't change anything in the other rows. So I established my 1. That means I want to establish zeros in these two spots. Well, lo and behold, I already have a 0 in the third row in that position. Great. That's what I wanted. So all I really need to do is make a change to turn the second row into an equation that has 0 as its X term as well. So I'm going to take row 2 and subtract away 2 times row 1, because 2 minus 2 times 1, 2 minus 2 times 1 is going to give me that 0 I need there. but I have to make sure I do that for all of the entire row. So space out a little bit more. 1, -5, 0 being 17, 0, 1, -4 being 13. Those aren't going to change. So again, 2 minus 2 times 1 is going to give me the 0 there. 1 minus 2 times -5 is going to become 1 plus 10. That's going to give me an 11. 1 minus 2 times 0 is still going to be 1. -3 minus 2 times 17. Well, 2 times 17 is 34. So -3 minus 34 gives me a -37. So it looked like for a second there, it's like, oh, we already, I mean, a lot of students will try to like say, oh goodness, we also had our 1 already here too. Unfortunately, to get the 0, that had to go away. And as you can see, when I add or subtract a multiple of another row, I'm going to probably change things. I'm going to change things across the entire row. And in many cases, something that I may have already changed to a 0 or may have been a 1 will get undone. So I'm not undoing anything here, because if I follow this procedure correctly, the rest of this procedure, I'm not going to have anything go on differently here. That's going to stay the same. So I'm going to do one more row operation at this point. I want to now establish the 1 that I had over here. Now I don't want to add a multiple of another row, because that's not going to help me here. You know, unless I choose to do a multiple of row 3, that won't affect my 0 at all. But it's just easiest to say, okay, well, I have 11 there, so if I essentially take row 2 and I divide it by 11, or multiply by 1/11, so I'm going to get what I need there. So this column, well, first of all, row 1 and row 3 are not being affected by this row operation, because it's only affecting row 2. 0 times 1/11 is still 0. So notice again, my column of 1s and 0s have remained unaltered. 11 times 1/11, 11 times 1/11 is going to give me the 1 I want. So 1 times 1/11 is going to give me 1 over 11. -37 times 1/11 is going to give me a -37 over 11. And in many cases, you are going to get some pretty gnarly fractions along the way. Well, now what I want to do is I want to get a 0 here and a 0 here. I established my 1. And anything I do beyond this point should not change this one. Those 2 that I just highlighted in orange, they need to become 0s. So I'm going to define 2 row operations to accomplish that. I'm going to take row 1 and add 5 times row 2. The reason being is if I take -5 plus 5 times 1, that's going to become 0. I also want this 1 to become a 0, so I'm just going to say take row 3 and subtract row 1, because this 1 minus that 1 is going to give me the 0 I want here. And so with that being the case, I said row 1, it should be row 2. Yeah, row 2. So as I go through and do these, so row 1 and row 3 are going to be the ones changed here. This row will remain unaltered. If I look at this first row operation, row 1 plus 5 times row 2, I'll have 1 plus 5 times 0. That's still 1 plus 0, that's 1. So that's still a 1. Negative 5 plus 5 times 1. That's the reason why I did this particular operation. It becomes a 0. 0 plus 5 times row 2, or 5 times 111, is going to give me a 511. I shouldn't have a 0 here. (17) plus 5 times negative 37 over 11 becomes 2 over 11. Again, I'm not showing all the computations. However, you're responsible for being able to do those computations yourself. So make sure you practice your computations and using your calculator and whatnot. They'll obviously be a little easier to calculate on the final where you don't have the calculator, but right now you do have the calculator at your disposal, so do make use of it. Now I'm going to work on row 3, so I'm using R3 minus R2. So if I take this 0 in R3 minus this 0 in R2, it's still 0. So as you can see, nothing happened to this column. It's still my 1 and 0s in that column where they were before. Of course, 1 in row 3 minus the 1 in row 2 is going to give me a 0, which is what I wanted there. Negative 4 minus 1/11 is going to give me a negative 45 over 11. And 13 minus a negative 37 over 11 is going to give me, why did I put a negative 4 there? It's going to give me a 180 over 11. One of the things about doing this elimination method, is you're going to sometimes get some really nasty fractions and decimals. Dealing with denominators that you're not used to seeing. You're not going to have fourths and halves and things like that. You're going to have like sevenths and elevenths, and but they eventually do most often go away. So let's start with the now I have my first two columns established. Anything I do from here on out should not undo any of this. So as I now define my next row operation, I'm just going to bring it back over here. I want to make this into its 1. So I'll have my diagonal of 1s up to this point. So I had to think, well, what would I do to make that a 1? That's not going to change anything else I have in row 3. I don't want these zeros to change in any way either. So the best thing I can do for this is just simply multiply by the reciprocal. I'm going to multiply row 3 by negative 11 over 45. Which means this row is not being touched. This row is not being touched. And that should still be negative 37 over. I think this thing's glitching. I thought I wrote that before. And now when I get to this row, 0 times a negative 11 over 45 for both of these is still going to give me zeros in those positions. Negative 11 45 times negative 45 over 11 is going to give me the 1 here. That's what I wanted. 180 over 11 times negative 11 over 45 is going to give me a negative 4. So as you see again, nothing changed with these two. I've established my 1, and anything I do from here on out shouldn't change that either. So I have to think what I need to do to get the zeros in the last two places, namely here and here. Well, I'm going to add multiples of row 3 now because it has the zeros in the first two columns and only has something going on in the third column, which means that if I add, well, in the result columns as well, if I add multiples of row 3, then nothing's going to change except the third column of row 1 and row 2 as well. So row 1, I'm going to subtract away 5/11ths, row 3, and row 2, I'm going to subtract away 1/11th of row 3. And when I do that operation, row 3 is going to be left untouched. One minus 5/11ths of that 0 is going to be 1 minus 0. It's still going to be 1. 0 minus 5/11th of row 3. 0 minus 5/11ths of 0. It's going to still be 0. 5/11ths minus 5/11ths times 1 is going to give me the 0 here, which is what I wanted. 2/11ths minus 5/11ths times -4 ends up giving me a positive 2. Second row, this 0 minus 1/11th of 0 is still going to give me 0. 1 minus 1/11th of 0 is going to give me still 1. 1/11th minus 1/11th times 1 is going to give me the 0 I want here. Negative 37 over 11 minus 1/11th of -4 gives me a -3. And so what these equations are telling me now is that, again, I have 1x plus no y's plus no z's equaling 2, which basically means that x equals 2. This one's saying I have no x's, 1 y, no z's equaling -3, which basically means y equals -3. And 0 x's plus 0 y's plus 1 z equals -4, which basically means that z equals -4. So our solution is 2, -3, -4. Under most cases, I'm not going to care if you use Gauss elimination or Gauss-Jordan elimination, or if you even use either one at all, because we're eventually going to learn other methods of doing this that you might find a little bit more pleasing, a little bit to the point. I personally find Cramer's rule, as far as a computational method where I had to show my work, probably being the fastest. But, that's what we have for our examples for this. And that also brings me to the end of this particular video. If you have any further questions, please make sure to bring them up in class or come and see me during my office hours. Until I see you in one of those places, or until our next video, I will see you around. Have a good day.